Welcome back. In this section, we're going to be looking at linear approximations and also at differentials. And the beginning of this all starts with the observation that if we've got ourselves a differentiable function, and if I've drawn myself a tangent line at the point x equals c to my function, that when we're close to c, the y values on my tangent line are close to the y values on my function. So if I wanted to estimate what is a value of f of x, and we're relatively close to what c is, so if I'm somewhere not too far off from c, then I can just use the y values on my line to estimate the y values that are on my curve. Of course, the opposite has to be thought of here too, that when things are further away from C, that the y values on the line and the y values on the curve won't be terribly close to each other. So that's something we'll have to keep in mind, is that if we're thinking about using our straight line to find approximate y values for our curve, we really only can do that when we're relatively close to that x value that we started with. Now, this is from the previous section, 3.8. We did a bit of work at the beginning of it and started off with the same sort of way, creating the equation of a tangent line at a particular point. And we got this, that if you are creating a tangent line, f prime of c, that is your slope, f of c, that is the y value, c, that's the x value for your point. So this is really all just coming from the slope point form of your line, where x1 is c, where the slope is f prime of c, and where the y value is f of c. So this is the equation that would give me the y values that are on my straight line, that are on my tangent line. But we also said as long as you're relatively close to c, f of x, the actual y value on the curve, can be approximated by that y. So if I wanted to figure out what is f of x, that is approximately f of c plus f prime of c times x minus c. Again, we're going to have to be cautious when we use this and make sure that we're picking a value of c that's relatively close to the x that we're interested in. The closer we can get, the better of an approximation we'll get. And that's a little note that I make there. For an approximation to be good, we need to pick an x value that is close to c, or rather pick our c that's close to x. Also, we have to be cautious of any discontinuities. If you have a discontinuity between where you draw your tangent line and where you're interested in, things can get a little bit off. The example that I have here is 1 over x. So suppose I were to draw my tangent line at 1/2, and I use that to figure out what is the approximate value at negative 0.1. On my tangent line at negative 0.1, the y value would be something very big and positive, but the actual y value at negative 1 is something large and negative, and there's quite a big difference between them. And the reason why my tangent line approximation is so wildly off is because the function has a big discontinuity at x equals 0. We have a vertical asymptote. So provided we're dealing with a nice continuous function, though, then we can be pretty confident in using a linear approximation. Okay, so now I'm going to do a bunch of little linear approximations. So each time I'm going to start off with the function, I'll figure out its derivative, and then I'll think about which point that I'm going to use, what is the c that I'm going to choose. I've got the square rooting function here, so that's my f of x, square root of x, and I know the derivative is 1 over 2 root x. So I know that if I were looking for square root of 83, I can do that by using a point that's close to 83 that I can find a square root of. So you've got a couple of choices. You could choose 81 because square root of 81, that's a number we know, that's 9. Or you could choose 100 and square root of 100, that's 10. That's another number we could choose. I'm going to go with the closer one because, again, the closer x is to c, the closer that my number is to 83, the better of an approximation I'll get. So I'm going to use my c value to be 81. So if I want the square root of 83, that should be f of c plus f prime of c times x minus c. So we wind up with 9 plus 1/18 times 2, or 9 in the ninth, which in terms of decimals is 9.1111 repeated. The actual value for square root of 83 is actually not too far off. Square root of 83 is 9.110435 and some other stuff. So, 2 decimal places are actually correct with this approximation. So that's a pretty decent approximation. Okay, cosine of pi over 12. This is one that you could find the exact value of if you felt clever and you wanted to use some trig identities, but here we don't want to find the exact value. We're just looking for something approximate. So again, I'm going to think about first, what is the function? Well, that's my cosine function. And then what's my derivative? Well, that would be negative sine of x. And then, of course, if I'm thinking about what am I going to choose as my value for c, who can I find a value that's close to pi over 12? So pi over 12, that's 15 degrees. You could choose 0. You could choose pi over 6. Either would be relatively fine to use. So I'm going to be really lazy here and choose 0. Why not? So in this case, I would find that cosine of pi over 12 is approximately equal to f of c, which is cosine of 0, plus f prime of c, negative sine of 0, times x minus c, pi over 12 minus 0. And cos of 0 is 1, and we'll wind up with plus 0 times pi over 12, which is 0. So we wind up with 1 as our approximate value for cosine of pi over 12. I'm going to do another one just because why not? What if you chose instead, maybe you might choose pi over 6 because that's another one. I could evaluate f and f prime at pi over 6 without too much difficulty. So if I chose that one, I could say, well, cosine of pi over 12 would be approximately cosine of c, so cosine of pi over 6, plus negative sine of pi over 6 times pi over 12 minus pi over 6. And so when I do a little bit of churning out with that, pi over 6 for cosine, that's root 3 over 2. Sine of pi over 6, that's a half. Pi over 12 minus pi over 6, that's negative pi over 12. And then I run that through my calculator and I get about 0.9969251, somewhere like that. The actual value is actually really close to both of those. So if you actually calculated cosine of pi over 12, it turns out to be 0.96592 and some other stuff after that. So both 1 and 0.996 are relatively close to the exact value. So not too bad on either side. Okay, one more. This one, I mean, squaring isn't that difficult, and you could do this easily enough by hand if you really felt like it. 6.125, squaring it, sure, why not? But if you wanted to be a little fast and come up with an approximation, you could say, well, if my function is the squaring function, then the derivative is 2x. And if I chose my c value to be 6, then 6.125 squared should be approximately f of c, which is 6 squared, plus f prime of c, 2 times 6, times x minus c. So 6.125 minus 6. So when I do that, I get 37.5. And if you came up with the exact value and put in what is 6.125 and squared it, you would get 37.51562. So my approximate value is actually pretty close to the exact value, and it's way faster than doing all that multiplication unless you have a calculator handy. Just one thing I wanted to do for fun: what if you chose a really bad value? So here I chose 6, which was really close to 6.125. What if I chose 1 as my value for C? Because I decided to be really lazy and said, oh, 1 would be really easy to put inside of f and f prime. It's not very close to 6.125, but who cares? What if I decided to just go wild? So in that case, I'd run into a problem, and that's this. When I put in 1, so I'd have 1 squared plus 2 times 1 times 6.125 minus 1. When I calculate that out, I get 11.25, which is nowhere close to the true value, or nowhere close, rather, to the true value of 37.51562. So just because you can find an approximate value doesn't mean it's necessarily a good one. This one is a terrible approximation, and not a big surprise because I chose a value for C that was quite a ways away from the value I was looking to approximate.